modulus of complex numbers. In previous exercise, we have saw properties of complex conjugates in exercise 2.4. That is totally 10 properties of complex conjugates, and we have derived totally 7 sums. In exercise 2.4, we have derived totally 7 sums. The first 3 sums and iteration is given in one video session. Next sum number 4, 5, 6, 7 is given in another video session. We have finished exercise 2.4, properties of complex conjugates. Now we are entering the important side of complex number, nothing but modulus of a complex numbers. This is very, very important. In this chapter we can expect 1 5 mark also. Very, very important exercise, modulus of complex numbers. First we are going to see the introduction part in modulus of complex numbers. In this introduction part, first I am going to speak about the modulus. What is my modulus? Suppose in lowest standard we have studied modulus of 3. Modulus of 3 is nothing but 3. Modulus of 3, this is not determinant, this is a modulus. Modulus of 3 is nothing but 3, and modulus of minus 3 is also plus 3. The minus will become plus. The minus will become plus. I am speaking about simple modulus only. I am not speaking detail about x is less than 0, x is greater or equal to 0. I am not speaking about. Simply I am going to speak modulus. What is my modulus in lowest standard? Modulus of 3 is nothing but 3, and modulus of minus 3 is equal to 3. Nothing, I am going to choose only the positive values. Why? What is mean by modulus? First of all, what is mean by modulus? The modulus nothing but the distance between the origin and 3. The distance between the origin and 3 is nothing but 3. For example, if I am going to take one graph, this is x coordinate, this is y coordinate. So, if I am going to choose modulus of 3, the 3 is going to present 3. If I am going to take 3 here, the distance between the origin and the 3 is nothing but this is 3. Suppose if I am going to take minus 3, the distance between origin and this minus 3, even though this is negative value, the distance is going to be positive, so it is going to be 3. The simple definition, the distance between the origin and the number, the distance between origin and this number, this is called modulus. Simply you can say it is an absolute value also. Sometimes it was another name was absolute value. The simple definition, the distance between the origin and the number, the given one, the distance cannot be negative, no. So only minus 3 will become plus 3. So this is the easiest one. For example, if it is in xy plane, it is in xy plane. Suppose the same modulus is present. The same modulus is present in complex numbers. What will happen? So now we are going to see the modulus for complex numbers. The very, very interesting introduction. So listen. So for example, if I am going to take 4 plus 3i, this is a complex number. 4 plus 3i modulus. 4 plus 3i modulus. Since it is a complex number, I want to take real, this is 3i, okay, 3i. I want to take in real and imaginary, real line and imaginary, real and imaginary. So this is minus real, this is minus imaginary. So we know this is 1, 2, 3, 3 and 4. This is 1 is nothing but I. This is 2i, this is 3i, this is 4i, but I am not going to place I, so leave it as it is. So 4 plus 3i, you can able to find the distance easily in number line, no problem, x and y plane, no problem. In complex number, are we going to find the distance? Suppose that is modulus of 4 plus 3. It is simply used for modulus of 3 is 3, modulus of minus 3 is 3. I have told the distance between the origin and the number, this is called distance. If it is, even though it is negative, the distance cannot be negative, so only plus 3. So I am going to use it modulus of 4 plus 3. The distance between origin and distance between the origin and 4 plus 3. The distance between origin and 4 plus 3 is the modulus. So this is real 4. This is imaginary 3. The 4 and 3. This is real. This is imaginary. Both will coincide here. 4 and 3. This is nothing but 4 plus 3i. The point is 4 plus 3i. Still we need to find the distance. So from the distance between the origin and the point, this is nothing but modulus of 4 plus 3i. This is distance. The distance between the origin and the point 4 plus 3. This is nothing but modulus of 4 plus. This length is nothing but modulus of 4 plus 3. How we can find? So I am going to draw a straight line. So it becomes going to be hypotenuse. This is opposite. This is adjacent. this distance is going to be 4. This is 3. So this also going to be 3. You know hypotenuse square. Hypotenuse square is equal to opposite square plus adjacent square. Here hypotenuse nothing but 4 square plus 3 square. 4 square 3 square is nothing but 25 hypotenuse square. So hypotenuse is nothing but 5, because hypotenuse square is 25 and hypotenuse is 25. This is going to be 5. The distance is going to be 5. So this is called geometrical representation. I am representing this one as geometrically. Suppose I am going to take. So we have found the distance between the origin and the complex number. So only we are using the modulus. The distance between the origin and the complex number is nothing but 5. How? Using the Pythagoras theorem. So we have put in answer is nothing but 5. You can take some other examples also. For example, 12 minus 5i. You can take 12 minus 5i. What is the distance between the origin and 12 minus 5i? So I am going to take real and imaginary. This is real. This is imaginary. The 12 real will be here. 12. This will be a 12. So from here to here distance is 12. Imaginary is minus 5i. So it can be a minus 5. I don't need to put I. So minus 5. So 12 here minus 5 here. So coinciding point is this one. 12 minus 5i. 12. The point is 12 minus 5i. So you need to draw the distance between the origin and the point 12 minus 5i. This one. So join this. So if this from here to here minus 5 means this also minus 5. The distance cannot be negative. So you want to write plus 5. So this is hypotenuse. This is the distance. The distance between the origin and the point is nothing but modulus of 12 minus 5i. I need to find the answer for this. So how? 2 hypotenuse square, nothing but 12 square plus 5 square. 12 square 144, 5 square is 25, is nothing but 169. 169 square is nothing but 13 square. So answer is going to be 13. So distance is going to be our 13. So 13 is our distance between the origin. The distance between the origin and the complex number. The distance between the origin and complex number is nothing but 13. The distance between the origin and the complex number is nothing but 13. So how easily we have found the distance between the origin and the complex number 12 minus 5a is the distance 12 minus 5a 13. So this is nothing but distance between the origin and complex number, but they are giving some formula for that. They are giving some formula for that. For example, how we can do? The formula is nothing but 4 square plus coefficient of imaginary 3 square. 4 square plus 3 square is nothing but 16. 16 plus 9 is square root of 25. Square root of 25 is nothing but 5. So we have got the answer. Without using the Pythagoras theorem, we can use one formula. The same here also. 12 square, nothing but 12 square plus 5 square. So nothing but 144, 25, 169. 169 is nothing but 13. Without using Pythagoras theorem, you can find. So what is the formula? Now I am going to write this formula. The formula is nothing but z is equal to x plus iy. If I am going to use modulus of z is equal to modulus of x plus iy. Is nothing but x square plus always plus y square. X square plus y square. This is the formula. X square plus y square. Square root of x square plus y square. Without using Pythagoras theorem, you can use. For example, z is equal to real plus imaginary. Modulus of z is equal to modulus of real plus imaginary. Simply you can say is equal to real square plus imaginary square. Imaginary square. Real square plus imaginary. This is the formula. Real square always plus imaginary square. For example, z is equal to 12 minus 5i. Modulus of z is equal to modulus of 12 minus 5i. Nothing but square root of 12 square real square plus always plus imaginary is minus 5. So minus 5 the whole square. You should not put minus here. So nothing but 144 plus 5 square is 25. Square root of 169 is nothing but 13. Suppose z is equal to 5. Only real is present. What will be modulus of z? Modulus of z is equal to modulus of 5. Modulus of 5 straight we can write the answer. Without using real square plus imaginary square, we can write straight the answer is nothing but 5. If we want real square also, what? 5 square. Square cancel, once again 5. But z is equal to 5i is present. 5i. So modulus of z is equal to modulus of 5i. So what is the answer is going to be? Real square is absent, only imaginary square is present. 5 the whole square. Square is nothing but 5. This is also 5. How we can represent here? We can represent here. So z is equal to 5. Z is equal to 5. 5 is present real. The distance between the origin and the number 5 is nothing but the distance is a 5. You can easily say the answer with seeing the graph. Suppose 5i. 5i is nothing but imaginary. This is real, this is imaginary. What is the distance between the origin and the 5? Nothing but distance 5. So this only we have got. Answer is 5. You can easily say. Otherwise, if you are going to get z is equal to 12i or minus 12i, z is equal to minus 12i. Modulus of z is equal to modulus of minus 12i. So you know real square, there is no real absent, plus real square is 0 square, plus imaginary is minus 12 the whole square. So square root of minus 12 the whole square is 144, nothing but 12 square is nothing but 12. So if we are going to take this negative part, this is nothing but minus 12. From here to here distance is 12. Even though it is minus 12, the distance cannot be negative, so the answer is going to be 12. So what is our modulus? If I going to put modulus, real plus imaginary, if I going to get one complex number, real plus imaginary, modulus of z is equal to real square plus imaginary square. Always plus should be real square plus imaginary square. Don't forget real square plus imaginary square. I will represent in graph also how to find the distance between the origin and the complex number. I'm going to explain the geometrical interpretation of distance between two complex numbers. So I'm going to take let two complex numbers be z1 and z2. Let two complex numbers be z1 and z2. So I'm going to take a geometrical interpretation. So this will be real, this will be imaginary. Suppose if I'm going to take from here to here, I'm going to take point z1 here, z1, point is z1, real and imaginary z1. I'm going to take another point as z2 here, point is z2. This is real, this is imaginary. So the distance between from here to here and distance between from here to here. So I want to say one thing, important thing. I need to find the distance between z1 and z2. I need to find the distance between z1 and z2. So how am I going to find the distance between z1 and z2? Nothing but if I going to draw one line, I am going to draw another line parallel to this line. So this will be z1. The distance from here to here will be modulus of z1. Listen, this is the point z1. This is the point z1. This is the distance between origin and z1 is modulus. Distance itself modulus of z1. So once a distance or length comes to here, distance or length, I need to put modulus. From here to here, the distance is modulus of z1 because it is z1 no, then modulus of z1. In previous also I have showed you. The point is 4 plus 3. This point is 4 plus 3. The distance from here to here from nothing but modulus of 4 plus 3. The point is 12 minus 5a. From here to here distance modulus of 12 minus 5a. The same usual method only. The point is from here to here is z1. The distance between from here to here is nothing but modulus of z1. I have pointed the point z1, the same line, the line which is parallel to modulus z1 from here. Draw one parallel line. For this is a parallel line. If this is modulus of z1, this is also modulus of z1. If this one is modulus of z1, this is also modulus of z1. So this line is z2. Draw a line parallel to z2. So from here to here, this is a modulus of z2. If this is modulus of z2, this also distance will be modulus of z2. So this point is called z1 plus z2. This point is called z1 plus z2. So I need to join this one. The distance will be modulus of z1 plus modulus of z1 plus z2. So this is nothing but modulus of z1. This is z1 point, this is z2 point, distance is modulus of z1, this is modulus of z2. Draw a line parallel to modulus of z1, this one. Draw a line parallel to modulus of z2, so this is modulus of z2. Draw one triangle, draw a triangle. So this is the resultant distance between the z1 and z2. So modulus of z1 you can add, that's all. You can add. So summing the distance between z1 plus z2. This is a point z1 z2. This is adding z1 plus z2. So next, now we are going to see properties of modulus of complex numbers. So we are going to see the properties of modulus of complex numbers. The first property, modulus of z is equal to modulus of z bar. Modulus of z is equal to modulus z bar. So we can take some example. If z is equal to 4 plus 3i, easy example. What will be z bar? 4 minus 3i. In previous exercise we saw, if z is 4 plus 3, modulus z bar is 4 minus 3i. Now I am going to take modulus. Modulus of z is equal to modulus of 4 plus 3i. What is the answer? Real square plus imaginary square. Real square plus imaginary square. So answer is nothing but 25. Answer is going to be 5. The same here, take modulus of z bar. Modulus of z is equal to 4 plus 3. Modulus of z bar is equal to modulus of 4 minus 3. First you write real. Real is 4 square plus imaginary is minus 3. Minus 3 the whole square. This also minus 3 the whole square plus 9, 16, 25. 25 is nothing but 5. So both are same. So what is from this what we have learned? Modulus of z is equal to modulus of z bar. This is the first one. Next, second property. Second property is nothing but modulus of z1 plus z2 is less than or equal to modulus of z1 plus modulus of z2. This is called triangle inequality. Triangle inequality. Very, very important. Very, very important proof. Triangle inequality which is present in the page number 66. Very, very important one. Triangle inequality which is present in page number 66. Very, very important proof. So modulus of z1 plus z2 is less than equal to modulus of z1 plus modulus of z2. So we can prove this, no problem. So I decide to prove this. So how I am going to prove? I will take this rough column, very easy. If you are going to see modulus of z1 plus z2 is less than or equal to modulus of z1 plus modulus of z2. So I am going to take z1 is nothing but 1 plus I. z2 is nothing but 2 plus 2i. I assumed z1 is nothing but 1 plus. I am going to take LHS alone. What is LHS? Modulus of z1 plus z2 is equal to, first is z1 plus z2, add z1 z2, 1 plus 2, 3 plus I plus 2i. At present, in spite of I will take 2i, it's very easy, 2i. So 2 plus 2, 4i, 4i. So real square plus imaginary square, 9 plus 16, nothing but 5 is answer. LHS. If I am going to take RHS, RHS is nothing but modulus of z1 alone, modulus of z1 plus modulus of z2. So this is z1. What will be modulus of z1? Real square plus imaginary square. This is a real square 1 square. Imaginary is 2. 2 square is nothing but 2 square. You write 2 square itself. z2 real square 2 square. Imaginary is also 2 square. So this is square root of 5. Square root of 5. This is square root of 2 square is 4. 2 square is 4. Nothing but 8. If I go into take square root of 5 is nothing 2.4 something. Square root of 8 is nothing but 2.8 something. Just one assumption only. This is 2.4 something. This is 2.8 something. So what is the answer is going to be? See, 8 plus 4, 12, carry over 1, 2 plus 1, 2, 2 plus 1, 4, 5.2, 5.2. So the answer we got, this one answer is nothing but 5. 5 is less than or equal to 5.2. Yes, 5 is less than 5.2, not equal. So when the answer will be equal? When the number is going to be only real. For this also I am going to give you some example. For example, z1 is equal to 5, z2 is equal to 4. Only real number is present. If real and imaginary is present, or imaginary is present, real imaginary present, and the answer will be less alone. When equal symbol will be present, when only real or only imaginary is present, it will be less. So LHS. What is LHS going to be? Modulus of z1 plus z2. Add 5 plus 4, 9. Modulus of 9 is 9. RHS. What is RHS? Modulus of z1 plus modulus z2. So modulus of z1 is 5 is 5. modulus Z2, modulus of 4 is 4, answer is going to be 9. So this one is equal, LHS, RHS are equal. For this one is, this value 5 is less than 5.2. So this, when real and imaginary is present, will be less. When real is present, it will be equal. This is less than or equal to. We have got less than or equal to. The main important third property. The important third property is modulus of Z1 minus Z2 is greater or equal to whole modulus. Modulus of Z1 minus modulus of Z2 and whole modulus. This is whole modulus. You need to put whole modulus. This modulus is very important. This is very important. Using these two expressions and formulas only, we are going to solve 2 to 3 sums. So better I am going to combine these two properties, combining property 2 and 3, combining the property 2 and 3, nothing but see here, Z1 plus Z2 is less than modulus of Z1 plus Z2. Modulus of Z1 minus Z2 is greater than whole modulus Z1 minus Z2. So surely how we going to write is nothing but first this one is very small, so write this one, whole modulus of Z1 modulus of Z2 whole modulus less than or equal to modulus of Z1 minus Z2 less than or equal to modulus of Z1 plus modulus of Z2, modulus of Z2. So the fourth property is very important property. Modulus of Z1 into Z2 is equal to modulus of Z1 into modulus of Z2. Modulus of Z1 into modulus of Z2. The fifth property, modulus of Z1 by Z2, we can write as modulus of Z1 divided by modulus of Z2, comma Z2 is not equal to 0. Z2 is not equal to 0. Otherwise it becomes infinity. The sixth property is modulus of Z whole power n, we can write as modulus of Z whole power n, where n is integer. N is integer. The seventh property is real part of Z is less than or equal to modulus of Z, and eighth property, imaginary of Z is less than or equal to modulus of Z. This will be very useful to solve some sums. Real part of Z is less than or equal to modulus of Z. Imaginary part of Z is equal to less than or equal to modulus of Z. Modulus Z. You can prove this. You can prove this if you want. You can prove and see. So the ninth property. If I want to find the distance between Z1 and Z2, you know distance formula. Distance is equal to square root of x2 minus x1 the whole square plus y2 minus y1 the whole square. The same distance formula. If Z1 is equal to x1 plus iy1 and Z2 is equal to x2 plus iy2, I can find the distance nothing but modulus of Z1 minus Z2 is equal to square root of x1 minus x2 plus y1 minus y2. X1 minus x2 and y1 minus y2. You need to place square here and here, no problem. You can write x2 minus x1 also, no problem, because it is whole square, no, x2 minus x1, the same x2 minus x1 you can use also. In most, because I written z1 minus z2, z1 minus z2, so x1 minus x2 whole square plus y1 minus y2 the whole square. This is must. This is must. This is very must. For example, if z1 is equal to 4 plus 3i and z2 is equal to 3 minus I. So distance, modulus of z1 minus z2 is equal to modulus of, first put modulus of 4 plus 3i minus 3 minus I, modulus. Now you can solve this sum very easily. This is very important. Distance between two components, z1 minus z2, just put modulus z1, write z1 minus z2. So mod 4 minus 3 is 1, minus 3i, minus into minus plus 3i plus I is 4i. Now you can write real square, 1 square next to 4 square. 16 square root of 17 is our answer. This is very easy. You don't need to follow this formula also. Better you follow this formula. This way, this procedure. Z1 minus Z2. This is distance between two complex numbers. Very, very important. Distance between two complex numbers. Modulus of, you need to put modulus of z1 minus z2. Distance between two complex numbers. Modulus of z1 minus z2 is equal to modulus. Okay. Next, the final one. Modulus of z square is equal to z bar. This is very important. Listen carefully. This is very important one. Modulus of z square is equal to z bar. Modulus of z square is equal to z bar. Very important. This property is very important. Modulus of z square is equal to z bar. So within this we are finishing the properties of modulus of a complex numbers. Next we enter inside a sum. Okay students, we have detailing undergone the introduction of properties of modulus of complex numbers. After investigation about that, we need to enter exercise 2.5. The first sum, find modulus of the given complex numbers 2y divided by 3 plus 4i, the first subdivision. Solution. So I need modulus. So modulus of 2y divided by 3 plus 4i. We have studied one of the property is nothing but modulus of z1 divided by z2. We can write as modulus of z1 divided by modulus of z2. Condition z2 is not equal to 0. This is one of the formula, one of the properties we have studied. The same thing we need to separate the modulus for numerator and denominator. Modulus of 2y divided by modulus of 3 plus 4i. You know, modulus nothing but real square plus imaginary square root of real square plus imaginary square. Here real is absent, so 0 square. Imaginary coefficient is 2 for 2 square divided by here square root of real square is 3 square. Imaginary is 4, so 4 square. So 2 square is 4. Square root of 4 divided by, this is square root of 25. Square root of 25. Square root of 4 is 2 and square root of 25 is 5. So answer is 2 by 5. Next, second subdivision. We move towards second subdivision. The same first sum but second subdivision. In this 2 minus i divided by 1 plus I plus 1 minus 2i divided by 1 minus I. In this sum, just like a previous sum, we can't put the whole modulus. It is not a good way. Modulus, this is not a proper way. We can't able to put whole modulus. We're going to put whole modulus also waste only. So first we simplify the value. 2 minus I divided by 1 plus I plus 1 minus 2i divided by 1 minus I. Now just we need to make a cross multiplication. This moves here. 2 minus I into 1 minus I plus cross multiplication 1 minus 2i into 1 plus I whole divided by 1 plus I and 1 minus I, 1 plus I and 1 minus I is equal to 2 into 1, 2 into minus I, minus 2i, minus I into 1, minus I, minus into minus plus, minus into minus plus, but I into I square is value minus 1, so put minus 1. Next, plus 1 into 1, 1 into I is I, minus 2i into 1 is minus 2i, minus into plus is minus 2, I into I square value is minus 1, here minus plus, so put plus, whole divided by 1 plus I, 1 minus I, format of A plus IB, A minus IB, A plus IB, A minus IB, format is 1 plus I, 1 minus I, 1 plus I, 1 minus I. So coefficient of A is 1 and coefficient of B is 1 only. So 1 square plus 1 square. So answer is going to be, so 2 minus 1, 1, otherwise minus 1 plus 1 cancel, 2 plus 2, 4. Next, minus I plus I gets cancelled, minus 2i which gives minus 4i divided by 1 plus 1 is 2. I can take 2 outside. If I am going to take 2 outside, 2 minus 2i divided by 2, 2 gets cancelled. Now I can take modulus. Remaining is 2 minus 2i, take modulus. Modulus of 2 minus I divided by 1 plus I plus 1 minus 2i divided by 1 minus I. This value is nothing but modulus of 2 minus 2i. You know real square, 2 square, imaginary minus 2 the whole square. Real is 2, imaginary is minus 2. So answer is going to be 2 square is 4, minus 2 square is also 4. The answer is 4 plus 4, 8. This 8 I can write 4 into 2. So square root of 4 is 2, remains only square root of 2. So this is the required answer. 1 minus I whole power 10. Find the modulus. Solution. Modulus of 1 minus I whole power 10 is equal to, we have studied one formula, z n modulus nothing but z modulus whole power n, the same format. 1 minus I whole power 10. This 10 moves outside the modulus. So we know real square plus imaginary square. Real square is 1, 1 square. Imaginary is coefficient of I is minus 1, minus 1 the whole square. Still whole power 10 is present. So 1 square is 1, minus 1 square is 1, whole power 10. Nothing but square root of 2, whole power 10. So how I can write this square root of 2? This 2 I can write as 2. This square root I can write as 1 by 2. 1 by 2 into 10. This square root I can write as 1 by 2. I can cancel both this. 5. 2 power 5. 2 power 5 is nothing but 32. You can write stop here answer, or you can stop here answer, no problem. So both are correct answer only. Next, finally, the fourth subdivision. This is the last sum in the first sum. Last subdivision in the first sum. 2i, 3 minus 4i, 4 minus 3i. Solution, I need to use modulus. Modulus of 2i, 3 minus 4i, 4 minus 3i. Close the modulus. You can put separate modulus. Modulus of 2i, modulus of 3 minus 4i, modulus of 4 minus 3i is equal to square root of, real square is absent, imaginary is 2 square, square root of 3 square is 9, minus the 4 square is 16, 4 square is 16, and 3 square minus 3 square is 9. Square root gets cancelled, answer is 2. Square root of 25, square root of 25, 2. You know square root of 25 into square root of 25, which gives 25. 2 25s are 50. For example, square root of 2 into square root of 2 is 2. The same square root of 25, square root of 25 is nothing but into 25. So 2 25s are 50. Within this we can stop our first sum. So we will move towards the second sum. Second sum. For any two complex numbers, they are given two complex numbers. The first complex number is z1 and second complex number is z2, such that modulus of z1 is equal to 1 and modulus of z2 is equal to 1. Modulus of z1 is equal to 1 and modulus of z2 is equal to 1, and z1 z2 is not equal to minus 1. Then to prove that z1 plus z2 divided by 1 plus z1 z2 is a real number. Solution. First to prove is very important. z1 plus z2 divided by 1 plus z1 z2 is real number, is real. You know the formula for real. Real is nothing but if z is real, if and only if z is equal to z bar. This is the formula. If z is real, then we can say z is equal to z bar. They are given one condition. Before first we take this condition, modulus of z1 into modulus of z2 is equal to 1. Modulus of z1 and modulus of z2 is equal to 1. Now you can write modulus of z1 is equal to 1 and modulus of z2 is equal to 1. Modulus of z1 is equal to 1 and modulus of z2 is equal to 1. Now squaring on both sides. Same here also, squaring on both sides. After squaring on both sides, modulus of z1 square is equal to 1 square. Modulus of z2 square is equal to 1 square. So you know modulus of z1 square is, you know one formula. What is the formula? Modulus of z square is nothing but z bar. This is one of the property. I told you it's very important property. Modulus of z square is equal to z bar. What is present here? Here z1 is present. So I can write z1 bar. Z1 bar is equal to 1 square is 1. The same here also, modulus z2 square. So z2 square, how I can write? Z2 bar. So z2 bar 1 square is 1. So keep this condition as it is, otherwise you can write z1 bar is equal to 1 by z1. This 1 by z1 comes down. The same way also z2 comes down. z2 bar is equal to 1 by z2. This condition is very, very important to solve this sum. Nothing but z1 bar is equal to 1. This z1 comes down, 1 by z1. z2 bar is equal to 1. This z2 comes down, 1 by z2 bar. So within this condition, I am going to derive the sum. Before derive the sum, I am going to choose let z is equal to z1 plus z2 divided by 1 plus z1 and z2. If I am going to show this z is equal to z bar, then it is going to be real. So keep it, this is must. The substitution plus z, final answer should be is equal to z bar. Then answer z is equal to z bar means it should be z is real. So this is now taking conjugate on both sides. Taking conjugate on both sides. Taking conjugate on both sides. Z bar is equal to z1 plus z2 divided by 1 plus z1 z2 the whole bar. Here also taking bar, here also taking the whole bar. This whole bar I can take it as z1 bar plus z2 bar divided by 1 plus z1 bar z2 bar. I can separate the bar for each and everything. So z bar is equal to z1 bar. What is z1 bar? See here, what is z1 bar? This one. What is z1 bar? 1 by z1 plus what is z2 bar? 1 by z2 divided by 1 plus what is z1 bar? 1 by z1. What is z2 bar? 1 by z2. 1 by z2. So cross multiply. z2 moves here. z2 into 1 is z2. z1 into 1 is z1. z1 into z2. z1 into z2. Whole divided by this z1 z2 goes here. z1 z2 into 1 is z1 z2. 1 into 1 is 1 divided by z1 z2. We can cancel z1 z2. So z bar, listen, z bar is equal to, arrange it properly, z1 plus z2. z1 plus z2 divided by 1 plus z1 z2. 1 plus z1 z2. Listen carefully. Therefore z bar is equal to what is z1 plus z2 divided by 1 plus z1 z2. z1 plus z2, 1 plus z2 is nothing but z. So we have got z is equal to z bar. Therefore which implies z is real. That's all. Hence proved. Very, very important sum. But the main concept is, listen, we need to show z1 plus z2 divided by 1 plus z1 z2 is a real number. Since we know one concept, z is real if and only if z is equal to z bar. I need to show z is real. If z is equal to z bar, then z is real. They given one condition, z1 modulus of z1 is equal to modulus of z2 is equal to 1. I apply equal to 1 equal to 1. Squaring on both sides. Because of square only, the formula comes for us. Squaring and squaring. Modulus z1 square equal to z1 bar equal to 1. I need z1 bar to bring down z1. The same here also. After let assumption, we need to assume this one as z. So z is equal to z bar means z is real. I need to get z bar here. So taking conjugate both sides, we are going to proceed this sum. We can get answer very easily. Third sum, which one of the points 10 minus 8i, 11 plus 6i is close to 1 plus I. It's close to 1. Whether 10 minus 8i is close to 1 plus I or 11 plus 6i is close to 1 plus I. So simply I need to find the distance between 1 plus I, 10 minus 8i distance, 1 plus I, 11 plus 6i distance. Which distance is very least, that point will be very, very closest. So first I am going to find distance. Distance from 1 plus I, complex number 1 plus I to 10 minus 8i. 10 minus 8i. In one of the sum we have saw, want to find the distance between nothing but z1 minus z2 is equal to distance. To find the distance nothing but this is, if I go and take this one as z1, this one as z2, nothing but z1 minus z2 is equal to z1 1 plus I minus, as it minus I need to open the bracket, 10 minus 8i, close the bracket. So modulus 1 plus I minus 10 plus 8i is equal to 1 minus 10 is minus 9, plus I plus 8 is nothing but plus 9i is equal to square root of minus real square plus imaginary square. Real square plus imaginary square, what comes? Minus 9 square plus 9 square. Real square plus imaginary square. 81 plus 81 is nothing but 162. Otherwise I can take 81 plus 81. 81 plus 81 is nothing but 162. This 162, square root of 162, this can be written as 2 into 81. 81 is nothing but 9. Square root of 9, 9 into root 2. This is one distance. Otherwise I can keep this square root of 162. This is better one. Keep square root of 162 as it is. The final answer next. Distance from 1 plus I to 11 plus 6I. 1 plus I to 11 plus 6I. The same formula. This one is Z1, this one is Z2, Z1 minus Z2. 1 plus I, open the bracket, 11 plus 6I, close the bracket. 1 plus I minus 11 minus 6I is equal to 1 minus 11 is minus 10, I minus 5 minus 6 is nothing but minus 5I, close the modulus. So take square root of minus 10 the whole square plus minus 5 the whole square. This is 100, this is 125, nothing, this is 100, this is 25, nothing but 125. Now check the answer. This we can write as 25, 125. This is I can 25 into 5, nothing but 5. For 25, 5 root 5. But better answer is this one. I need to take this one, square root of 125. Listen carefully. This one is must. Take square root of 125. Take square root of 160. If you want, you can put box also. Take this one. Square root of 162, square root of 125. Which one is the least one? Square root of 125 is the least one. So this one is 1 plus I is 11 plus 6I is nearest to 1 plus I when compared to 10 minus 80 to 1 plus I. So the 11 plus 6I is closest to 1 plus I. This is our final conclusion because this is the least. 125 is least. Square root of 125 is least. Square root of 125 is least when compared to square root of 162. So within this we finish this video session. We will start our 4, 5, 6, 7, 8, 9, 10 on the next video session. Thank you.